doesn't matter. I'll try my best.
So yesterday, I was away at a meeting, and I missed you guys too. And I asked Mr. Kirkland, the sub in here, to show you kind of what went on first period. And I'm just curious how that went for you guys. Was it easy to understand? Did it go too fast? Were you able to get down the notes that you needed to? Yeah. Are there any questions before we kind of pick up with the symmetry stuff a little bit more today that you want to clarify from yesterday? Were there any questions that kind of popped in your head as the video was playing yesterday, like, oh, I wish she could clarify this, or I wish I could ask that? Not sure if we wrote them down or not. Maybe flip through the pages, see if anything jogs your memory. Yeah?
For the y equals x symmetry, will it always be like that's the slope, or will it always be the slope of 1?
It'll always be 1. Yeah, so for the diagonal y equals x symmetry, it's always that perfect, like, 45-degree angle line. Yep. We're pretty good from yesterday? Okay, well, we're going to continue on page 96, just trying to test whether these functions have a particular type of symmetry. And when you went over number 1 from yesterday, notice how you could have more than one type. So maybe you have origin and x-axis symmetry. Okay, so it is possible to have more than one. That's why we have to kind of test each possibility. So we're going to pick up today with number 2. And maybe you can reference number 1 from yesterday or some of the previous pages if you have to. What was the special ordered pair relationship if we had an origin symmetry? That was the graph that we could flip upside down and it would be exactly the same. Good, Elsie? Negative x, negative y. Okay, so you can start with any point you want, x comma y, and if the graph has origin symmetry, this other point, negative x, negative y, would also be on the graph. Okay, so they're specifically related to each other. So we're going to take this point and substitute it into the equation. So it looks like we have to make every y negative, but also every x negative. When we simplify it, we're interested in seeing, do we get the same equation or do we get something different? Okay, if we get the same equation, we know that this point matches up perfectly with the original. Okay, they're exactly the same if you were to apply the symmetry to the graph. So what about negative y to the 4th? If you were to do negative y times negative y times negative y times negative y, what would that simplify to? Go ahead, Hadley. Positive y to the 4th. Okay, for the other ones, if we multiply the negative x, they're just going to switch signs. So is the result we get the same as the original equation we started with? Not exactly the same, right? I mean, the y to the 4th is the same, but the 2 and 3x's are not. So since we do not get the same result, the graph of this equation, whatever it might look like, because we have no idea, whatever the graph looks like, it does not have origin symmetry. So you are not able to flip it upside down and it would be exactly the same. So let's go ahead and see if it has any other type of symmetry. What about that special ordered pair relationship for the y-axis symmetry? Go to Olivia? Yeah. Negative xy. Okay, so in this particular type of symmetry, the x value switches sign. So in the equation, we only really have to substitute in a negative x. Notice how the y would stay the same. It's still a value of y. So simplifying, looks like the x terms would become negative. And that's clearly not the original equation that we started with. So this graph, whatever it looks like, does not have y-axis symmetry. What's on the left and the right do not match up. Okay, there's something different. What about the diagonal symmetry? Go ahead, Lincoln.
Y comma X.
Y comma X. Okay, so the values switch. So for every Y, we'll plug in an X, and for every X, we'll plug in a Y. Is it the same equation? No. All right, so there's no diagonal symmetry either. We're starting to wonder if there's even any type of symmetry at this point. Okay, so because we're running through our list. What about x-axis symmetry? Go ahead, Lincoln.
X comma negative Y.
X comma negative y. Okay, so the x's stay the same. We just have to plug in a negative y. And when we simplify it, we already said negative y to the fourth would change to a positive y to the fourth. Is that the same equation? Yes. Okay, so this graph, whatever it looks like, has x-axis symmetry. You can take the top half and fold it down over the x-axis and it would match up with the other part of the graph. Okay, so it does have some type of symmetry. What else do we know about this graph or this equation if it has x-axis symmetry? Yeah? It's not a function. Good. It would not pass the vertical line test. Okay, not a function. Is that a good review from yesterday? Do you guys think you can try the next two? 3 and 4 at the bottom? See what you get. Test each type of symmetry. Not necessarily. Because, for instance, this graph had origin, right? But if you fold it left and right, it wouldn't match up. And if you fold it very high, it wouldn't match up. So, which one? This one? That's a cube root possible.
Oh yeah, I guess it would depend on the
No.
I don't know, so we're going for M now.
Why X?
Since you go to Y, that's X is that's the next grade Y, so you do that.
So it could just have one, it could have...
It does.
What matters? It's just making a deal of saying.
The order?
Minus.
Yeah, you have to do it in that order. Yes, it matters.
Sometimes you calculate, it's like, no one's
In that order as well.
If you don't do it correctly,
Sometimes you can't get
you're
it.
gonna do
This
it.
graph,
No, I
whatever
do.
it looks like.
Why is that order wrong?
Cause I don't like it.
It's too bad.
I like origin, x-axis, y-axis, and then y-axis.
It's not Y of X, it's Y equals X.
Same thing. But not.
No, definitely not.
So since it has the,
Why might be
I like mine. It's all in order, like yours.
no, I have everything mine in the same order, except. This one is not a function. I mean, X-axis.
What? Who doesn't have it in the right order? No, you don't.
I'm gonna put this on the
Now you're talking about
Unless you like wrote it down accidentally. Wait, no, you have.
No, he doesn't.
What's wrong?
Yeah, I know.
This is the right order. Orgy Harry.
I regret
You're like,
every day not sleeping.
he's like, that sucks.
And then I do it again the next night.
Very bothered.
Have any time.
Really bothered by that. Wait, what? Wait, it would make sense if x-axis went after y-axis, and then it would be y-axis. It really doesn't matter.
What do you see? It's just X, Y.
It's Thursday.
Wait, Thursday, go.
Thursday is week. Theodore.
But like, it's like, it's your X and then Y in a coordinate. So X and then Y.
I guess I can figure that out tomorrow.
Genius.
I don't know, I like that order a lot better.
Blair, are you gonna take the
I just don't like this being here. Because like, look at it from the negative side. Look at the negative side. Double.
Oh, yeah, I guess that's it.
And then it's like,
Negative, negative. Negative, positive. Positive, negative. Not negative, negative. Negative, positive. Positive, positive. Positive.
What is that? Maybe it's good.
No, it is not.
I wrote the wrong one.
All right, I was walking around and they looked pretty good. I definitely want to go over 3 because it's involving an absolute value that we didn't necessarily discuss in here together, but it seems like most of us got the hint. Origin symmetry, if you plug in negative x and negative y, I think we're familiar that this would change to a positive x squared. If you take the absolute value of a negative, that becomes a positive, right? So instead of negative y, you can change it to positive y. And notice how that is exactly the same as the original, so we do have origin symmetry. If you tested the other values, it looks like the y-axis symmetry would work as well, and also the x-axis symmetry. But the diagonal symmetry does not match perfectly. So this graph, whatever it looks like, has 3 different types of symmetry, how you can rotate it or fold it in specific ways. How do we do with 3? You want to go over it any more than that? No? What else do we know about this graph or this equation? It's not a function. Good.
That's homework.
You mean test the symmetries for a piecewise function?
Like, test to see if, like, the entirety of the function itself, like, the overall thing.
For piecewise functions, it can get tricky because it would depend where the pieces are located and if they would match up. So I would say the only way to really test it for a piecewise function would be to graph it. That way you see that visual. All right, what about 4? Can we breeze through this? Did we have origin symmetry? Did the equation match perfectly? Yeah? What about y-axis? Yeah? Diagonal? Yeah? X-axis? Yes? Which means it's not a function, okay? Let me ask you this. Can you think of a graphical shape that would have all 4 of those types of symmetries? A circle, okay? Not sure if you recognize it or not, but this is the equation for a circle. X squared plus y squared equals something. Okay, so this is the equation for a circle. Can we identify the radius? 5. Good. Okay, we'll eventually be talking about circles later this year. Maybe you remember that from geometry, maybe not. Okay, but we'll be diving deeper into that later on. Okay, so if you think about it, a circle centered at the origin would have all 4 of those types. You can flip it upside down, it's exactly the same. If you fold it left and right, they would match up. If you fold it diagonally, everything would match up. And you fold it top to bottom or low to high, it would match up. Everything checks out. What's that? Notebook from last year when you did circles? Nice. All right, we are going to extend our symmetry concepts into our next section today. So let's take a look at page 99.
What are we doing on Thursday? Can I just like
There is no tomorrow.
I don't know just yet. That's why I left it blank.
We're gonna play Jeopardy.
All right. Can we classify the different types of symmetries for these graphs? I know you did a little bit yesterday, but just want to do a little bit more practice. Can you classify the type of symmetry for f of x? It could have more than one, okay, but can we start somewhere? Yeah?
Y-axis?
Y-axis, definitely. Okay, if you fold it left and right, the sides would match up. What about g of x? Is there some way you can fold it to have things match up, or can you rotate it 180 degrees and it would be exactly the same? Rotate? Okay, if you actually wanted to try it, flip it upside down, it would be the same graph. Okay, so this would be our origin symmetry. What about h of x? Is there some way you can fold it, or can you rotate it? Rotate it? If you flip it upside down, it would be the same graph. Okay, so origin symmetry. What about p of x? Yeah? Y-axis. Okay, left and right, if you were to fold it, would match. What about r of x? We thinking diagonal? Maybe? Let's see. If we were to take this point and fold it over diagonally, I think it would land here. So it would not match up with that one. So that's not perfect diagonal symmetry.
What would you say it was? It is. Yes, it's.
I'm sorry that.
Can we fold it or can we rotate it?
Rotate.
Rotate it. If you flip it upside down, it would be the same graph. Okay, origin symmetry. What about q of x? Reflective, specifically y-axis. Okay, so what I'm trying to get to with these examples is even though we have 4 different types of symmetries, like we did in the last few examples, there are 2 major ones, okay, ones that show up more often, and those are y-axis and origin symmetries, okay? The x-axis symmetry is nice to identify, but remember if we have y or x-axis symmetry, it's not a function. And that's something that we're not really concerned about, right? We're normally used to working with functions. So x-axis doesn't happen that often. The diagonal symmetry, okay, is interesting. We're going to dive a little bit deeper into that later on in the unit. But we're specifically going to take a look at y-axis and origin symmetry a little bit more in this section. I would say these are the more common types, okay, these 2. So on the next page, now that we identified which one of these were y-axis and which ones were origin, I want to take a look at this a little bit further. And to save us some time from flipping back and forth, I want you to take a few minutes to copy down these ordered pairs. So if you were to write down f of x, p of x, and q of x, because those were the graphs that we just identified as y-axis symmetric graphs, these would be the ordered pairs on the graph. Again, to save us some time from flipping our paper, take a few minutes to copy down these ordered pairs. bless you. All right, so these were the graphs on the other page that we labeled as y-axis. These were the graphs that we labeled on the other page for origin. And these are some special ordered pairs. Like if you were to look at the graphs again, they would be the big kind of bolded dots. Okay, we're going to take a look at those ordered pairs. Let's see. Erica, can you do me a favor and pick any point you want from the P of X table? -2, 0. Okay, so Erica picked a point x comma y. Can we find a related point to that one that she chose? Is there another point in that table or column that looks similar to that one? Good, Maggie?
2.
And how are those related together?
They have the same y coordinate.
They have the same y coordinate, but what's different?
Y stops.
The x is the opposite. Okay, so let's see. Olivia, can you do me a favor? Pick a point in the Q of x column. -1, -2, right? So Olivia picked a point, and according to our y-axis relationship, there should be a related point where the x is the opposite and the y is the same. Does that happen? Right there, right? X is opposite, y is the same. It doesn't matter which point you pick, okay? I could have picked -6, 4 in the P of x, and notice how there would be the related point. So it doesn't matter where you start with, okay? If we have y-axis symmetry, there should always be a related point to the one that you pick, okay? And hopefully this looks familiar because this was a special point we used when we were testing symmetries, like going through all 4 possibilities. What about for the origin values? Robbie, can you pick one for us from the G of x column?
-2, -2.
-2, -2. All right, so Robbie picked some beginning point. Is there a related point to that one he picked? Can we find it? Probably 2, 2. And it looks like both values switched. So we'd have -x, -y. Let's see. Elsie, can you pick one for us from R of x? -1, -2. So if that's the point she picked, there should be a related one where both coordinates switch sign. And notice how that's there. Okay, so there's our special point, a relationship for origin symmetry. Now, since, as I mentioned before, these are the two more common types of symmetry, these are a little bit more special. We have certain vocabulary terms or words that we use to mean y-axis symmetry or origin symmetry, and those terms are on the next page. So, even function, actually we'll get there in a moment. Let's write this down. For y of x symmetry, we said if we had the point x comma y, the related point would be -x comma y. And for origin symmetry, if we picked a point x comma y, the related point would be -x, -y. All right, so in terms of vocabulary, instead of saying it is a y-axis symmetric graph, okay, that's kind of a mouthful, there's a lot of words to say. Instead of saying it's a y-axis reflective graph, you can simply say it's even. You see how much shorter that is? So we're using vocabulary terms to represent kind of larger phrases or ideas. So when we say a function or a graph is even, that means the same thing as having y-axis symmetry. So when I say even, you automatically know you can fold it left and right and it would match up. Just some other things to jot down here. If we know it has y-axis symmetry, we know this point relationship where the x is opposite but the y's stay the same. What we're going to try to do is convert this point relationship into function notation, like actual mathematical language. So let me ask you this. If you know the point x comma y is on your graph, how can you use that using function notation, like f of x? Can we write what that would look like? I'm asking you a very loaded question here. This is definitely a thinker. If you think about an ordered pair, the x is the input, right? And the y is the output. So in terms of a function, okay, whatever f it might be, you would plug in x and you would get out y. Does that make sense when we write it that way? This is normally your input and your output is what it equals in the end. We can write a similar statement for the other point. If you plug in negative x, you get out y. So if this is a function notation to represent this ordered pair, and this is another function notation to represent this ordered pair, maybe we can bring the two together. Let me ask you this question. If both of these values equal y, what do we know about those values themselves? If they both equal y, then what do we know? Can we think about it? Can we do some type of substitution? If y equals this function notation, can I plug that function notation into that other y? Aren't they the same thing? Yeah? So if I were to plug this function notation over here, it looks like I would have f of negative x, okay, this left-hand side, equal to f of x. If they both equal y, they both equal each other. Does that make sense? They're the same? Okay, so we're amping it up a little bit. So when I say even function, you know it's y-axis symmetry. Since it's y-axis symmetry, we know we have this relationship between the points. And if we start to write and talk mathematically, this point relationship can be written as such. So from now on, okay, if we see this notation, f of negative x equals f of positive x, that's cluing us into an even function. Okay, it might be a little difficult making that transition, but we'll get there. Okay, I promise. Let's try odd function. Okay, so this is representing origin symmetry. I think this is a little bit easier for us to remember or recognize because origin, odd, they both start with O. So instead of saying a graph has origin rotational symmetry, you can simply say it's odd. Okay, so it's a lot shorter phrasing. If it has origin symmetry, we know we have this relationship between the ordered pairs. Okay, we saw that from the previous graphs. And if we want to step it up a bit, start to write mathematically, we can transform or rewrite the way these ordered pairs are written into function notation. So for the first ordered pair, we plug in x, we get out y. For the other point, we plug in negative x, we get out negative y. We can merge the two together to write one equation or one value here. So if y equals f of x, we can plug that into this y, into the other value. So f of negative x would equal negative f of x if we make that substitution. So they can be kind of confusing. Again, function notation, we're not too familiar with it, or we are for certain circumstances, but now we're starting to amp it up a bit. When you look at them, they are very similar. Notice how they both have f of negative x, but it's what they equal that's different. Okay, either you have a positive f of x or a negative f of x. I know it might be going over our head. Okay, that's okay, because tomorrow we're going to look at this a little bit more in depth. Okay, how do we know if this is true or if this is true for certain equations or graphs? Okay, but for now, the main idea I want you to get is that even means y-axis and odd means origin. Okay, new vocabulary for us to recognize it in this section. Okay, we'll stop there for today, and we'll pick up some more examples tomorrow.